Hello friends, welcome to the Engineering Projects YouTube channel. I am Mariam. We have started the series of Electronic Devices and Circuit Theory by Robert L. Ballasted. This is the chapter number 1 of our series and its name is Semiconductor Diodes. Today we will discuss about Zener Diode and it is the last lecture of our series, and in the Zener Diode this is the last lecture of the chapter number 1, and in the Zener Diode we will discuss about Zener Diode definition, its symbol, its figure, its characteristic curve, avalanche, difference between the avalanche breakdown and the Zener breakdown, and some important properties. So what is Zener Diode? Simple, the silicon p-n junction device designed to operate in reverse biased region is called Zener diode. So it is important. It is the normal silicon as the p-n junction device, and it is used to operate in reverse biased. It is important. It is used to operate in reverse biased region is called Zener diode. So normal device when heavily doped, then it will become Zener diode, and when we use it in reverse biasing region, then it will operate the main function of Zener diode. So it is highly doped device. It is the normal, it is the figure of normal diode, and it is the figure of Zener diode, and you can see here it is lightly doped and it is heavily doped. When we have two types of doping, pentavalent and trivalent. Okay, when pentavalent doping is applied to then we have electrons, and when trivalent doping is applied to silicon or germanium, then we have this p side structure, we will have holes, and this is the normal diode. And when we apply the when we increase the doping level, then we will have more electrons and more holes, more electrons in n region and more holes in p region. This is the symbol of Zener diode. The symbol of Zener diode is like the normal diode, but here we will have the Z-like shape, not the simple line at n side. So in this case, when we have n type and p type, and we combine both n type and p type, and then in this case electrons will move from this region to this region, and we will have positive charges here and negative here, and there will set up an electric field. Electric field direction will be from positive to negative. In this region there will be a electric field and its direction will be from positive to negative. There will also be the electric field. In this case we will have less number of positive and negative signs. In this case we will have more number of positive and negative signs. So here the electric field will be strong E, weak E. Now we will discuss about avalanche breakdown and Zener breakdown. Lightly doped diode plus wide depletion layer. You can see here it is the lightly doped diode and its depletion layer is wide. When we let us apply the reverse biasing voltage. P type is connected to negative terminal of battery and n type is connected to positive terminal of battery. Reverse biasing voltage is applied. When reverse biasing voltage is applied, then our depletion layer width will increase and we will have the width like this. And when here in Zener diode the reverse biasing potential is applied, again the width of depletion layer will increase. But this increase in depletion layer in comparison of normal diode is very small. In both cases, the width of depletion layer will increase when diode is reverse biased, but this depletion layer width increase will not be too much. It will be lightly doped and wide depletion layer. Here the depletion layer is white. It is heavily doped with narrow depletion layer. Electric field is not strong enough to produce the Zener breakdown. In this case, electric field will exist, but this electric field will not too much strong. But here the electric field will be very strong, and this electric field will breaks the covalent bonds. Strong electric field across the narrow layer. This is the narrow layer, and across this narrow layer we will have the strong electric field. Minority carriers collide with semiconductor atoms in the depletion layer. Here this is the N type and it has holes. There will be the electrons, and these electrons will be the minority carriers in the N type, and these electrons when collide with the semiconductor atoms, here this is the depletion region, and this depletion region contains the silicon atoms, and when these electrons will collide with the silicon or germanium atoms, they will produce the in the depletion region and breaks the covalent bond and produce electron hole pairs. These free pairs create the avalanche of charges. Let us consider this is the electron. This electron will move into the depletion layer, and in this layer it will collide with the semiconductor atom and it will breaks the covalent bond. When the covalent bond breaks, then the electron hole pair will produced. When this single electron will produce an electron hole pair, then when electron hole pair is produced, then there will be two electrons. These two electrons will produce 4 more electrons, will collide with 4 semiconductor atoms, will collide with 2 semiconductor atoms and produces more 2 electrons. So this will be the exponential process. One electron can produce number of electrons. One electron will produce 1 more electron. These 2 electrons will produce 2 more electrons. Then 4 electron will produce 4 more electrons, and this will be the exponential process here. So breaks covalent bond, electron hole pairs will be produced. These free pairs create the avalanche of charges. So avalanche of charges will be produced, and this avalanche of charges will cause the current to flow in this region, in the reverse biasing region. Because of these minority charge carriers, avalanche breakdown occur. Here the avalanche breakdown occur, and this avalanche breakdown will is the cause of the flow of current. Electric field ruptures the covalent bond. In this case, the strong electric field will rupture the covalent bond, and electron hole pairs are produced. So in this case, the electron hole pairs covalent are produced. Covalent bond is break because of the collision of minority charge carriers, but in this case the covalent bond breaks and the electron hole pairs produced because of the strong electric field. In this case, the minority charge carriers effect also occurs. It means we will have both effect. In this case, minority charge carriers also will also breaks the covalent bond, and the strong electric field will also break the covalent bond. So small increase in reverse biasing voltage will largely increase the current. When we increase the reverse biasing voltage, we will have the strong electric field. By increasing the reverse biasing voltage, the strength of electric field increases, and by increasing the strength of electric field, the ability to break the covalent bond will also increasing. And when the ability to break the covalent bond increases, the large current will flow. This large current leads to the Zener breakdown. So Zener breakdown occurs. Now let us discuss the characteristics curve. This is the characteristics curve, this is the forward biased region, and this is the reverse biased region. In the forward biased region, our diode, Zener diode, its p type is connected to positive terminal. For forward biasing, the condition is that our p terminal should connect to the positive terminal of battery. So P is connected to positive and N is connected to negative. It will have the voltage and the Zener resistance. The diode will have its own resistance, and this resistance will be equal to Zener resistance. So the function, this resistance will be equal to Zener resistance. In forward biasing, when RZ is negligible, then we will have the circuit diagram like this. This is the reverse biased region. For our characteristics curve, in this region, for this region we will have the circuit diagram, and in this region we can see very small amount of current is flowing. So here the resistance will be very high. So we can say this is our diode and it is in the reverse biasing condition. Its N type is connected to the positive terminal. So here the resistance level is very high and it will act as the open circuit. Now in this region, in this case, this is our diode which is also reverse biased, and it will have the battery like shape and the resistance, but here the current is flowing, it means the resistance can be neglected. So we will have the final circuit like this. At this point we have the voltage resistance VR, and it is equal to, and at this point the current value will be equal to IR, and it is equal to 10 microampere. This VR is the that, let us suppose we have a resistance which is connected in our circuit, and this VR is because of this resistance, and this IR is the current which is passing through the external resistance. At this point the knee breakdown occur. This is the IZ is for the Zener current and K is for knee. At the knee point, the current value will approximately equal to 0.25 milliampere, and at this point, which is the maximum current value, so Zener maximum current value will be equal to 32 milliampere. At this point we will have a Zener testing current IZT, and its value will be in between the IZK and IZM, any value. Breakdown voltage set by controlling the doping level. So if we increase the doping level, our breakdown will occur before. Our breakdown will be here, and if we increase more doping level, then we will have breakdown occur at this point, and if we decrease the doping level, our breakdown will be at this point. In forward biasing region, Zener diode acts like a normal diode. So you can see here, this is the characteristic curve for the normal diode, and in this region Zener diode act as the normal diode. So Zener diode important application is, it is used as the voltage regulator. So if we want to maintain 10 volt and our battery is not providing us the 10 volt, it is providing us 10.2, 10.3, 10.1, 10, 9.8, but when the Zener diode is applied, it will maintain the voltage level to a specific point. Then we will have 10 volt voltage, and so that's why Zener diode is used as the voltage regulator. So this is all for our lecture. If you like our lecture, then kindly subscribe our channel. Thank you.